Let me just say that we're very happy to have you down at Woods Hole, one of the broader MIT community, and I've been hearing for a long time about the amazing things that he's been doing, the amazing robots he's been doing, and he's recently been telling us that he's got lots of cool problems for robots. So I'm very excited to have you here today and hear your story. Yeah.
Well, thank you so much, Russ. Appreciate it. For those of you who don't know, I'm from Woods Hole, and Woods Hole is one of the few places which grants degrees which has both Woods Hole and MIT's name on it simultaneously. So we have this joint program where we take students, they're admitted separately both at Woods Hole and MIT, and in the ideal case, they have advisors both at MIT and Woods Hole and do joint research. And some of them are, of course, part of my group as well. So here's what I'm going to talk about today: bipolar robotics, both in the Arctic and the Antarctic. And really, what our group does is we're systems level people. So we work with the sensors, we work with platforms, we work with the algorithms, and we do it in the context of applications that have social relevance, or so we tend to say. And today, what I thought I'd do is really talk a little bit about the platforms and the algorithms, and some of the applications insofar as they illustrate what we're doing. And of course, the great thing about a small audience like this and something intimate like this is, feel free to drop me anytime. This doesn't have to be a one-way street. And I was an MIT grad student. Al Oppenheim is not here. If he were, I would say, he was the guy who made me, pick on students, and I would pick on him. But so please, if you don't pick on me, I'll pick on you. So I want to start off by telling you about a little bit about the first real expedition we did to the Arctic. Sure, thank you. And that was in 2007. And what you're seeing here is sometime in July at 85 degrees north latitude. That ship you see is the biggest ship I've ever been on. It's the icebreaker Odin. And what you can see is that it's been following this path, which is an open lead. You see it's broken ice right here, and here it is right now. Everything out here is completely covered with ice. This blue that you see is actually surface meltwater. This is still ice. And even a big icebreaker like this can't really break through ice. It has to follow these leads to go where it has to go. And the reason the Arctic's really interesting is also kind of neat is the Arctic Ocean is different from most other of the world's oceans. It's been isolated from the rest of the world's oceans for 65 million years. And it has outlets in Greenland and the Bering Sea to the rest of the world's oceans, but those are shallow water outlets. So the deep water in the Arctic has been isolated for 65 million years. And you say, all right, so what? Well, one of the other interesting issues is in 2003, there was an expedition. They were looking at a place called the Gackel Ridge, which is a mid-ocean ridge at the bottom of the Arctic Ocean. And they were looking at it as rock geologists. They were very interested in the rocks that come from there because it's a very slow moving ridge. And lo and behold, while they were doing that, they found evidence of hydrothermal vent activity. And that was completely unexpected. And it was unexpected in a couple of interesting ways. One, the conventional wisdom said that that ridge is moving too slowly, there should be no hydrothermal vents there. And the second thing which really excited people was that, hydrothermal vents is probably where life was at some of the earliest parts of this planet, because it was stable, temperature was stable, there was nutrients, even though it wasn't a photosynthetic system, it was a chemosynthetic system. So it's been around for millions of years. So what the biologists, the way they explained it to me was that, look, there's a science experiment been going on in the Arctic for 65 million years. Imagine the very basis of life evolving independently for 65 million years. Okay? It's a little bit like Australia. The reason we have all these marsupials in Australia is because Australia was isolated. But if the very origins of life were isolated for 65 million years, then that's kind of cool. And so there was a hunt to try and find those hydrothermal vents and see what they're like. Okay? And conventional technologies that we use to go to the world's oceans don't quite work. You can't really put a maximuscle there because you worry about the safety of the occupants. You can't put what we call ROVs or tethered vehicles down because tether management is really hard when you've got ice. You can't maintain your position. One of the interesting things about this ice is it's moving at about 10 centimeters per second, so it's moving pretty fast all over the place. Okay? And so, this is where we came in. We've been writing these proposals, and lo and behold, one of them got funded. And the basic idea was this: we will go out to the Arctic, we're going to go out to 85 degrees north. We're going to take a small robot. We're going to make a hole in the ice. We're going to dump this robot in that hole. It is going to swim down 4,100 meters, which at that time was the deepest any robot had ever been. Okay? It was going to do a survey of the seafloor, and then it was going to come up. And of course, about 18 or 20 hours would have taken place between when it first went in and when it was coming up. The ice conditions change. As I said, the ice moves at 10 centimeters per second. So in 20 hours, you move maybe 10, 15 kilometers away. We would fly a helicopter from the icebreaker, go search in the vicinity of where the vehicle was coming, see if we could find any open water, drive the icebreaker to it, and then drive the robot back to it. What could go wrong? Okay. And on a good day, things weren't very well. Because here it is, the vehicle's coming back after, in this case, an 18-hour mission, big huge fall. Actually, something did go wrong. Usually, we put a small boat in the water to go retrieve the robot, but the small boat was broken, so we had to drive on the surface for something to figure out. Okay, so that was great. However, on another day, here's what really happened. So we went out, we came back, we thought we had open water, and lo and behold, the wind changed, all the water closed up. So even though the vehicle was very close to us, we couldn't see where it was. One of the problems with it coming under ice is that the acoustics are really bad. So you might know that when it's in the water, that it's 100 meters away. But as soon as it comes to the surface, you have almost no idea where it is. And so we wound up, literally saying, okay, we'll take our chances, bring it up next to the bow, and we'll see if we can see it. And luckily, it didn't get in between, underneath an ice floe, but it came in between two of them and we could see it. And that's how we managed to go with that one. So, typically people say, here's what we did, here's our typical data, and what they're really trying to say is this is the best data we ever collected, but, that's typical data. But one of the things I want to tell you guys about is that, especially when you go out in environments like this, it's a hard problem. And, I want to share these lessons with you guys because we started off when we were doing these robotics, and we had the first law of underwater robotics. And the first law of underwater robotics says the number of deployments should equal the number of recoveries. Okay? If the number of deployments doesn't equal the number of recoveries, you're having a really bad day. Okay? And and that's true. And that's true. And once you do that 100 times, you realize there's a second law of robotics. And the second law of robotics says if you do 100 deployments and you have 100 recoveries, then you aren't pushing the limits hard enough. Okay, so it's okay to lose a robot once in a while. Okay, and so the interesting issue there is people often say, hey, what's your robot's name? Is it a cute name? And we like to say, hey, you name your iPhone. If you name your iPhone, go for it. But the way we think of these robots is as commodity items. The reason they're out there is to do things that we think are too dangerous for human beings to do. So if you lose one once in a while, it's okay. All right, it's a robot. And what did we find? This is again 2007. They found in 2007 they found 3 new volcanoes, which were huge. The biggest one of them was rising 1,000 meters off the seafloor that people had never seen before. So on our planet, we found a mountain 1,000 meters high, which nobody knew about. Okay, which is kind of fun. The other interesting thing we found is we didn't find the hydrothermal vents. Nobody's found them yet. We know they're there. Nobody's found them. But we found these microbial mats. And because we had biologists on board, we also had a little scooper, and we managed to get some samples. And of course, as soon as you get samples, you do DNA analysis, and lo and behold, they found 30 new species very high up on the tree of life. So they were very excited about that. So that was kind of cool. And of course, we did this all in the context of it was a high pressure expedition. We had all these press people. We had a TV crew on board, which all sounds really cool. It's really cool afterwards when they do a documentary on you. But when your vehicle's lost and somebody puts a mic in your face and says, how do you feel that your vehicle is lost right now? And you say, if I told you how I felt, you couldn't use it in your TV documentary anymore. Okay? And then you finally get out of that and you go up the bridge, and we were all gone for about 50 days. And we all had about an hour of satellite time to call home. And it's my daughter's birthday, and I pick up the phone and I call home, And I say, hi, Shipali, and she says, Dad, you lost your robot again. Because they've been following along on the webpage. So it's fun to talk about later. Okay. So let's switch gears a little bit. And you know, as we move from the Arctic, we go down. We go to someplace Caribbean. Enough of the cold. We've had enough cold in Boston. I'm going to move to someplace nice and warm. And one of the interesting things that we've been working on a lot of is fisheries. And I just want to show you a couple of images just to set the stage, as it were. Most of the time when you take images of the sea floor, they look like what you see on the top left. Okay? They look either green or blue, and reds tend to be attenuated very fast. And the reason is there's nonlinear attenuation of light underwater. Okay? So the reds get attenuated much faster, the greens less so, and so everything looks green. Okay? Now, if you start using regular 8-bit cameras, that's the best you can do if you were having a good day. And what we've been doing is really pushing the limits and trying to get, instead of getting more pixels, get more dynamic range. And what that lets us do is essentially homomorphic filtering, where we take the log of the image and we do high pass and low pass filtering, and we can get what we call true color. What would happen if we looked at the same scene in sunlight, drained the world's oceans, took a picture, and then quickly put the world's oceans right back. Okay? So that's the steps that we do. And of course, the one other big issue is, again, because of the attenuation of light, you can't move back far enough when you want to take a big picture of something, so you have to do mosaicing. Now, of course, panoramic mosaicing is pretty straightforward. You have an app on your iPhone that does that, but there's a few little gotchas when you're working underwater. Most of the gotchas are when you have a light source that moves with you, the shadows move, and the shadows are the strongest feature. And so a lot of the BCC equations don't really work, they fail, so you have to do something else. But it's very doable. Okay? So what I'm showing you is examples where we correct the imagery, put it together, and this is, of course, this is an ancient Roman shipwreck, 4th century AD in the Mediterranean. And this is the Titanic. The Titanic sank, let's get over it. But the point is, that's what we do with all our imagery. Okay? So we've really done something to our imagery even before we get to the next stage. And so one of the big issues here is fisheries. Now, fisheries, I have a friend who's a fisheries program manager, and one of the things she said to me was, Hanu, 150 years ago, there used to be professional hunters. They would go out and hunt buffalo and bring wild buffalo to the table for people who live in cities. And she says, what I'm afraid of is 150 years from now, the plight of fishermen is going to be like those buffalo hunters. That we won't be able to go out and get fresh fish caught in the ocean. Instead, we'll be farming everything, and that's all we'll be doing. Okay? And, and that's kind of scary. Okay? And so one of the problems with fishery is stock assessment. Basically, how much fish is out there? How much can you catch? And what do you do about that? And what traditionally people have been doing is they've been using what I call catch statistics. A fisherman goes out for 10 days on a boat which is very regulated, with a very regulated number of people, and if they catch 3 tons, they extrapolate and say, oh, there must be 300 tons in the world's oceans for that particular species. Okay? But when you get down to very low levels of fish, that's a nonlinear relationship, and that doesn't hold anymore. So nowadays, there's a big push to do something called fisheries independent catch statistics. They want to go out and figure out how many fish there are without actually catching them. Okay? And a simple way of doing that might be the following. Okay? You take a robot, you go out and you just drive along the seabed, and you get pictures of the seabed, and you count how many fish there are, and you can do some kind of statistics to figure out how many fish there are in the world. Okay? Now, what's wrong with that simplistic view? Well, the one good thing is, of course, you can get, 10 years ago when we started doing this, we were very data poor. Now we have these platforms, we built some for no fisheries, and we can literally collect millions of images. Okay? But the biggest problem, of course, is how do you go? The first thing that happens is they say, oh, we've never seen such beautiful images, we've never collected so many images before, and then they say, but what are we going to do with this? Okay? So the typical fisheries biologist, here's what they do. They take 100 images, they'll sit down with an Excel spreadsheet, and they'll take a marker and mark every little thing on that one image. Each image will take them 3 hours. And when they see 1 million images, they throw up their hands and say, why don't we subsample these and get 100 representative samples and just look at those, okay? And so the big push now is to say, how do we go from this data-rich environment to actually the information that people want, okay? And we can do it automatically, and we can do it in a computer-assisted way, so it's not automatic, but at least it's helping the operator. But, so here was, my challenge to one of my students, Nicholas, who is at NACI here, and what we agreed on is that his thesis would be called the 1 fish, 2 fish, red fish, 2 fish. Okay, he was going to count all the fish in 100,000 images, and he was going to get them down to the species level. Okay, and of course, despite my best efforts, his thesis title was more like the automated analysis and morphometric analysis of blah 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 blah. He didn't go for this. What he did do is he did a really good job on looking at one particularly important species called rockfish. Okay, and so he had a nice little algorithm. He basically took a hammer and just took all the image processing techniques that we could put together, feature vectors which were huge, implemented on our GPU, and got something that worked quite well, okay, for that one species. And there's some challenges. There are organisms which look like rockfish. The background can be pretty ugly, but basically that kind of works. Okay, so you get the rockfish in the imagery. You have a confidence measure about whether they are really rockfish or not. You can do some statistics and all this, and then you can use it for other things like finding crabs, for instance, which are also, again, what's nice about crabs, what's nice about rockfish, is if you've got a nice color enhanced image, they stand out. And they have nice shapes, so you can actually do something with it. Now, here's the problem, okay? One of the problems is, actually, I'm just going to show you this movie. You can see it for yourself. Okay, so this movie, just to give you some context, here's what we did. We took a camera, we sat it down on the seafloor, and we let it sit there for about an hour, so that all the fish, in this case it's a coral reef, were habituated to it. They don't seem to be disturbed by it. And then we took a robot and ran it through, okay? And so let's see what we saw. So here's the fish. It's speeded up a little bit, but there's lots of them, as you can see. They're all going all over the place. Suddenly they disappear, and then they come back. Okay, so I'm going to play this one more time, just so that you guys see it. Let's go back. And you could argue, the big question is, were they just naturally schooling? Did they actively avoid the robot? Were they attracted to the robot? I think they avoided it. Okay. And one of the interesting issues is, typically what we were doing is we were just taking the robot and looking at the imagery from the robot. And for various reasons, they like to have a very basic area where they can measure. And so they like to have a camera sitting right there, only in this area. They're not going to count anything in the periphery, not anything in the back. And the numbers we were getting from the robot were very different from the numbers we were getting from this camera. Okay? And so obviously, depending on the species, there's some species which are avoiding the robot and some which are attracted to it. And then we have this case, okay, where not only are these fish avoiding the robot in front of it right here, but they're also being attracted to it. Okay, so so this is one of the big biases we have, and we're still trying to sort this out. I wish I could give you a really good answer about how we can deal with this, but I don't know the answer. It's just the truth is these are the issues we have, and we're going to have to deal with them. But what's even more interesting,
Do you have a sense for it's the acoustics, if it's the hydrodynamics, if it's the...
I think it's all of the above. It's all species specific. So there are certain species, so one of the things we do is, for instance, we've also taken a sonar which looks forward, and then we've got a camera, and we can see this beautiful school of fish, and we see a vehicle come through, and they just bifurcate, go around the vehicle, and come right around. And then we've seen other fish which are just attracted to the, they just come feed. And then, it's also strobe duration. So one of our robots uses a strobe. That seems to not affect certain fish. If you have lights on for all the time, that definitely affects some fish. And usually, attraction way. So I think the answer is everything is species specific, unfortunately. I wish it was simpler than that. But even when they're not avoiding or attracting, there are some other interesting issues. And these are the issues that we are trying to get a handle on. So I think some of you may have seen this video. If you have, that's okay. This is for the people who have not. It's called Wow, You've Got to Be Good, right? And this is from my collaborator, Roger Hanumant. So that's an octopus, okay? And what that octopus was doing was camouflaging itself. It's a predator. It was just sitting there waiting, okay? And we're going to play this back. And now when you've seen him, he's going to become as big as he can to try and scare you off, okay? But let's watch this again. Okay, and of course, here's a couple of interesting things about the octopus. It's colorblind, okay? It's colorblind, and it's doing, of course, this is real time, okay? And so it's, I have a theory that it's doing 3D Fourier transforms in its head, but we'll get to that later, okay? Here's a static case, okay? Here's some images of skate. Can you all see the skate in here? Let's start with the top. The skate is right here. You see it? Right. Let's see if I can use a cursor. It's right here. It's kind of buried in the sand. Okay? And then in this one, there's flounder right here. You can see its eyes and its shape. And then in this one, there's actually two of them. There's a tail right here, and there's another one buried right here. Okay? And this is my favorite right here. Does everybody see the skate in here? I've got my cursor on it. And what about the second one? There's another one right on top of it. There's one right here as well. And maybe it doesn't project very well. But these things are so good at hiding themselves. Okay? And so here we've got, and of course if we were to do this in the original images, which were more green and black, we wouldn't even come close to seeing them. Okay? And so here we've got organisms which we can see. They're not warning us, they're not attracted to us. But if we miscount them, again, we've got all these biases that we introduced. So I'm going to play this game, okay? Let's see. It's called Spot the Octopus, all right? And John's busy, so we'll pick on John, right? Everybody knows John Leonard? John, you know where the octopus is in that top image? There's an octopus in all four images, so, anybody see the octopus? Let's start with, we're going to start with that one, we go there, and we go here, and then we go here. So up here, you see the octopus? Who sees the octopus? You see the octopus?
Lower left.
Lower left. Actually, no. Let's see. It's right here. You can see it's.
Nick spotted it.
You saw it, Nick? Okay. It's two
Yeah.
two eyes. And it's 3 eyes.
This one's kind of easy.
Okay. The second one is the easy one. Do you see it? Everybody see it? Okay. So here's its eye, and it's really big. What's kind of cool about the second image is worth noting is that it's not blending into the background. It's something different from the background. It's kind of figured out the textures that belong in this field, and it can only put on so many textures on its own bodies. So it says, here's the family of textures which are in the environment. This is the one that I can put on. Therefore, I should put this on, and it's artistic. And one interesting issue is it's in focus. It's right in the middle of the image, and it's encompassing a big part of the image, and it's still hard to semi-cover. Okay, everybody see it in here? Yes? No? What do you think, Russ? Okay, it's right here. Okay, you can see its eyes, and it's sitting right there. There. Did everybody see it in that one?
So how important is vision to this as a sensory signal for the rest of the fish and
It's pretty good.
It seems
It's
optimized for that, but I wouldn't have guessed it.
It is. I mean, in shallow waters, it's a really big deal, which is where we work with. So yes, really is a big deal.
Are there other sensory modalities that might make it easier to distinguish a soft-bodied animal from hard rocks?
Yes, and so people have typically been using acoustics, okay, and then they'll say, hey, we'll use an acoustic, but the problem is acoustics in a rocky habitat it's hard to distinguish rock from air bladder. Okay, and so that's the difference. So everybody see it here? Everybody see it here? No? There's actually two of them there.
Going on foreground.
Actually, John, you know, this is my made-up story. That's the null case. but the point I'm trying to make is that most of the world, sorry, most of the world is the null case. So you can't get in this mode where you're really looking for it and finding something when it doesn't exist. And most of the world is the null case. And when most of the world is the null case, you get conditioned not to find it. Okay, so that's another big issue. Okay, and you know, so the good news is, okay, believe it or not, I'm going to show you in the next few slides. These octopus, we actually now have a nice method for finding them. Okay, and so let's see, you know, what you guys think. So here's, I'm going to start with a reasonably easy one. It's right here in the middle. You can see its two eyes and its arms wrapped around it. Okay, we use just a, I would call it standard. This is, by the way, the work of Dr. Rashad, who's my collaborator at Los Alamos. And what he does is he's using a texture-based segmentation. Okay, and so he segmented the world into all sorts of little objects. And that doesn't really help you much more really, because you still don't know which of those objects is there. And then he does a simple operator, and the octopus shows right up. And just to give you a sense of what that operator is, we've left in all the bad ones as well. Okay, so it's actually saying that this is an octopus. All these things along the edge. Any idea what we're doing? So we've done the segmentation, and then we do something, and the octopus pops up. So what we're doing is, what is actually kind of interesting is, he looks at an object, and he looks at the boundary encompassing that object, and he does a ratio. And it turns out most organisms have a compactness requirement, either for heat or for some other reason. And so if this body, if this is smooth, that's a get giveaway that it's going to be something that might be worth looking at. And that's why you're actually getting all these faults, is because, you know, we have a better one where we take advantage of the fact that we're not going to use these straight line segments on the edges, but I left them in just so that you can see the straight line. So that actually works pretty well, okay, for the octopus. What about the skate? You know, here's the skate. Sorry, you had a question?
Does that fail when the octopus is like spread out?
So, you know, that's exactly what it's going to come to right now. Okay, so I think, you know, here's a little movie. Actually, before I go into the movie, you know, here's the real lesson we've learned with that whole segmentation problem, and it's true for the skate as well. Okay, is that we like to usually think of segmentation as a 0-1 problem. Okay, either there's an object or there's no object. Okay. Now, what we should really be thinking about is receiver operating curves. And I don't know how you guys are familiar with that or not. A good analogy is to think about the sonar. Okay. When I was taking IR Dyer's class right here, he explained ROC curves in the following way. He said, it's 1950s, the Russians are invading, a submarine's coming through, and you've got a sonar, and all that it shows on the sonar is it's basically an oscilloscope. This goes ping and ping. And the admiral comes in and starts next to the sailor and says, "Sailor, I want you to make sure that no Russian submarine gets by you." And the sailor says, "Yes, sir." And every time it goes ping, he says, "Submarine, submarine, submarine, submarine." Okay. So he gets every submarine, but his false positives just go through the roof. Okay. And the admiral's like, "Oh man, this guy's really pulling my leg. Okay, sailor, I want you to make sure that you never get a false positive." And the guy says, "Yes, sir." And every time he sees a ping, he never opens his mouth. Okay? So somewhere in there is you need to, from detection theory, you need to figure out how many false positives can you afford when you want your troops to come up. Okay? So it's a ratio, and that ratio is the receiver operating curve. So I think for problems like this, the conclusion we've come to is that we don't want to miss these organisms because they're important. But what we'd rather do is we present to a user all the cases that we can think of, including some that are going to be false positive, and let the user decide in the end. It's not a binary problem, it's an ROC curve problem. And where you want to be on that ROC curve is a function of what the user's end goal is. Okay, so this is still a work in progress, but I thought you guys would appreciate that. Okay, so let's move on. So, you know, you see polar bears here in the north, you see penguins here in the south. So this is 2010. We were in the Antarctic. And after we came back from the Arctic, we had a lot of interest in people who were interested in using our vehicles. I was at a conference and this guy came up to me and said, hey, Hanu, you know, one of the things we'd really like to do is take a vehicle, go on the ice, have a sonar look up, and make a measurement of the thickness of ice. And I was like, oh, great, okay, that sounds like a great plan. Why would you want to do that? And he says, well, you see, in the Arctic, we've had nuclear submarines go by for a long period of time. So we have a sense of what the thickness of the ice is. In the Arctic, the ice cover is shrinking. We know that. We can see that from the satellite imagery. In the Antarctic, the ice cover is actually increasing. Okay? And, you know, no, we're not global climate skeptics, but one theory is that even though the area is increasing, the thickness is going down, and therefore the volume is decreasing. Okay, we're getting a lot more first-year ice. It's not staying over the winter, and that's why, you know, that's what's going on. But we have no way of knowing because we don't have submarines from underneath. And if we make satellite measurements, there's snow on top of the ice, and that tends to depress the ice, and so you can't really make good measurements. And all right, great, that sounds good. I think we can do that. And I said, Jeremy, you know, you're British. How come you aren't using AutoCell? You know, because they have a really big program with beautiful AUV, which has done some amazing work. And he said, oh, we already asked them. They said it's too risky. Okay, so it's like, oh, that sounds great. So this is what we did. We went out, you know, we went out with our AUV, put it on the ice, on an icebreaker. Meanwhile, we were making measurements with airplanes and with satellites at the same time. Okay, and here's the traditional way that they used to make measurements of the thickness of ice. They'd go out with, you know, set up an area, and then they'll take drills, just like right here, and then manually drill a hole, and then they'll take a little line with a stick at the end of it, drop it in, pull it up, see where it gets stuck, measure that piece of line, and that's the thickness of the ice. Okay, and that's all sorts of problems associated with it. For instance, if you've got two blocks with water in the middle, you might be able to drill through the first block and you think you're in, you know, open water, there's more ice underneath, and you have got the wrong thickness. Okay? And whenever they get to really thick ice, like ice thicker than 6 or 7 meters, like they can't drill that deep, so they give up. Okay? So the right thing is a big part in the drilling measurements. And so
6 or 7 meters.
yeah.
I would have thought much more.
Well, what they wind up doing is they can drill deeper, but they want to do lots of holes. So what they'll literally do is they'll have a drill which is 2 meters. It's a meter drill with an extension on it. So they'll drill with that, hold it in place, take the drill off, put another extension, keep doing that.
I don't question their drilling ability. I just wonder. I thought that the ice would be a lot thicker than that.
So this is sea ice.
Okay.
So sea ice relative thickness is over the course of 1 year. Sea ice is probably grows a couple of meters. And then if it's multi-year ice, that's when it goes deeper, and usually it becomes thicker, and usually it's by rafting. So what happens is you've got first year ice, and you've actually, this is a great year to see it in Boston, because you see it near the harbor. All the ice gets pushed in, it gets stuck one on top of the other, it mounds up, and it, you know, all this stress and compression causes it to raft. And so that's where you get multi-year ice. And if it survives the summer, then it'll do it again, because there'll be more compression and more. And so, you know, 20, 30 years ago, there was a lot of multi-year ice. And now in the Arctic, a lot of the ice is just first-year ice. And you can also tell by its smoothness. For instance, if it's nice and smooth, that's first-year ice. Okay, and it's thin, it's nice and smooth, a couple of meters, that's first-year ice. Okay, and so here was the idea: you drop a vehicle in, and you take some measurements. And let's see this place. Come on. Here's just a little movie. So what they're doing right now is they're just drilling some holes. These are thicker holes where they're putting transponders in, so we can navigate underneath the ice. The great thing about ice is you can walk on water, you can walk out, go out and do it. This is the same icebreaker that I showed you earlier. After we did this with the British, we actually went out and did this with the Australians because they were excited about what we were doing. This is Clay Goons, one of our former graduate students. There happened to be a small little vehicle that they were using to just collect some samples on the ice, and that was in the water, and you'll see in a second. So you can see all the sensors are pointing up as opposed to down. We were interested in mapping the underside of the ice.
How much of what I consider to be the landmass of Antarctica is sea ice versus,
And that's actually a good question. There's about, it depends on where you are. So it might be, several hundred miles to, it might be just, land frost ice. So there's two different kinds of ice. Land frost is ice from the glacier, which is attached to the land and probably grounded. And then, or it might be just one contiguous block. And when you hear about the big icebergs forming, they usually form land frost ice. Like the Ross Sea Shelf is an example of land frost ice. And then the sea ice is just ice that surrounds it. And that can be as deep as 100 miles long. And it's stuff that people just haven't measured. When we first went in 2010, those were literally the first measurements ever made of the thickness of sea ice in Antarctica. And then this was in 2012 with the Australians. There's an interesting story. I'm glad you asked that question because one of the interesting questions that happened is the first time we go out and we say, hey, look, we're just going to put this vehicle in. Jeremy, we aren't so sure of what's going to happen. Let's find some easy ice so that if something goes wrong and the vehicle gets stuck, we can use the icebreaker to break it and rescue the vehicle out. He's like, yeah, this is first year ice. Okay, it's nice and smooth, it's 2 meters, we can break this very easily. Why don't you do your mission here? Okay, great. We do our mission, turns out the average thickness is 5 meters. And we come back and go, Jeremy, what was that about? He's like, oh, we made a mistake. It just looked like it was first year ice. Let's go somewhere else and we'll get you first year ice so that you guys feel better. And the second time we did it, it was again very thick. Okay. And and then that was our standard joke. Okay, yeah, this is first year ice. The sea ice guys, you have no idea. Okay. So we were coming back and they were really excited with all the data they had. And I looked at Jeremy and I said, okay, Jeremy, so we're gonna get our nature paper, right? And he said something which was really interesting. He said, nature papers are written about problems where people have been banging on a problem for a really long time and they know what the questions are. Out here, we're looking at the data for the first time, we don't even know what the questions are. And so that was kind of interesting. And even before we got back, he had sent emails to all his buddies, and one of them was an Australian they were planning on doing the same thing with their own robot. And they